Hey everybody, in this video we are going to be doing an example problem where we look at the energy transfers during one stroke of a piston. And to start us off, make sure that you have watched this video from Veritasium on YouTube about a fire syringe. This demonstration will help us look at the results we get in the end and try and make sense of them. So make sure you watch this video first. We're also going to break this example up into two separate videos because there are a lot of different pieces that go into it. And after those two pieces, we'll have a third follow-up video where we try and think through a little bit more conceptually what's going on. So here is the problem. We've got a 3 cubic meter ideal gas, initially at standard temperature and pressure, and it is placed then under a pressure of 4 atmospheres, which causes the temperature of the gas to increase to 28 degrees Celsius. So I'll remind you, STP stands for standard temperature and pressure, which is 0 degrees Celsius, pressure of 1 atmosphere. Now, 5 parts to this problem. Part A, what is the new volume of the gas? Part B, draw a before and after picture of this process, giving the values and labeling the relevant variables. Part C, under each of those pictures, draw a quantitatively correct energy bar graph, showing the energy that's stored in the system at that time. Part D, between the pictures, draw an accurate PV diagram for this process and use it to determine the amount of work or the amount of energy transferred into or out of the system through that working process. And then part E, between the bar graphs, draw a quantitatively accurate system schema for the process to determine the amount of heating. Now, the reason it's so many steps is because when you are encountering a problem, typically you're not given these steps A through E. You're just told to analyze the situation. So I wanted to give a bit more guidance here about what that analysis should look like. So part A, what is the new volume of the gas? So let's start there. I like to get my thoughts organized first, write down the variables in lists, separate out which is from state A or snapshot A, our initial snapshot, and which are from state B or snapshot B or our final snapshot. So snapshot A at STP, our temperature is 0 degrees Celsius or 273 Kelvin. Our pressure is 1 atmosphere or 101,300 pascals. Our volume is 3 cubic meters, and we don't know how many moles of gas we have. Snapshot B is at 28 degrees Celsius or 301 Kelvin. The pressure is 4 atmospheres or 405,200 pascals. We don't know the new volume of the gas. That's what we're trying to figure out in part A of this problem. And again, we don't know the number of moles, but we do know that it's going to be the same as what it was in snapshot A because there is no intake of new gas into the cylinder or exhaust of gas out of the cylinder. So 2 unknowns here. That's not going to be a good starting point. Snapshot A, 1 unknown. We can use the ideal gas law to find that 1 unknown. So PV equals nRT. I've given subscript A to our 3 variables, pressure, volume, and temperature. The R does not get a subscript because it is a constant, the ideal gas constant. And the N doesn't get a variable because it is the same in both snapshots. So we are solving for that N, so let's rearrange this equation to get N by itself on one side of the equal sign. And then let's plug in the values from the box above, and we'll keep in mind that the ideal gas constant R is 8.31 joules per mole Kelvin, and solving for all that, we end up with 134 moles. Now we know how much gas we have, so we can go over here to snapshot B and figure out the volume at that snapshot. PV equals nRT again. This time we're going to solve that equation for the volume at snapshot B, which is going to be nRT over P. Plug in the values from the box above and our 134 moles that we just found, and we end up with the volume at B being 0.827 cubic meters. Now, a few things to keep in mind with this analysis is that the temperature needs to be in the absolute scale of Kelvin. We can see a hint for that in that the units for our ideal gas constant are joules per mole Kelvin. But we can also see if we had used degrees Celsius over in this part of the problem, we would have had 0 in this denominator we would have been dividing by 0, which is not a good thing to do. Also keep in mind that since we're using this value of 8.31 for our ideal gas constant, which has units of per mole Kelvin over that joules there, the amount of gas needs to be in units of moles. So let's keep going. Part B, draw before and after picture of this process, giving the values and labeling the relevant variables. So let's sketch out some pictures. Picture of snapshot A. Here we go. We've got our cylinder. We've got our piston. Inside of the cylinder, we have some red gas particles that consist of the gas inside of our system. Outside of the cylinder, we have some gas particles in blue that represent the gas particles outside of our system. The pressure is 101,300 pascals, or 101.3 kilopascals, and the thermometer, the temperature reads 273 Kelvin. Now, a little note, a real pressure gauge would measure, well, the gauge pressure, how much above or below atmospheric pressure we are. So this pressure gauge would actually read 0 if it were a real pressure gauge because the gas is at 1 atmospheric pressure. But since we are going to carry out absolute pressure in our analysis, we're going to pretend that this is a gauge that measures absolute pressure and that is reading 101,300 pascals for us. Snapshot B. Here it is. So we should visibly see that the gas has been compressed because it went from 3 cubic meters over here to 0.8-ish cubic meters over here. So that's the thing in your sketch you need to make sure you show is that the gas has compressed. Our thermometer reading of 301 Kelvin and our absolute pressure reading of 4 atmospheres or 405.2 kilopascals. So those are our sketches. Part C, under each picture, we're going to draw a quantitatively correct energy bar graph showing the energy stored in the system at that time. That time meaning our 2 snapshots. So here's our picture we just drew, and we are now going to draw some energy bar graphs. First, let's start with an O in the middle of our LOL diagram where we define our system and where later on we can draw some flow of energy into or out of that system. So the system goes inside of the circle, which is going to be the gas inside of our cylinder, the red gas particles there. And then the gas in our surroundings, our environment, that's going to be outside of our system. Now we can draw some bar graphs to represent the energy flow. So here is the L in our LOL diagram. It's our internal energy at snapshot A. And let's just say it's 2 bars of energy, or 2 blocks of energy. Now, the internal energy at B. Let's think about this for a second. The temperature is a higher temperature. It's 301 Kelvin versus 273. The number of gas, so that means that any one individual gas particle on average has a higher kinetic energy at B than it does at A. We also know the total number of gas particles is the same in each. So if we have the same number of gas particles in A and B, and if on average each particle has a higher kinetic energy, then the internal energy at B should be a higher value. So let's go ahead and draw this as 3 blocks instead of 2, and we'll draw that added block. We'll put it in as purple to show that it's an extra block that came from somewhere. Now, it said quantitatively correct. Let's compute the amount of internal energy. 3/2 nRT computes your internal energy, N being number of moles, our ideal gas constant temperature at A being T subscript A. Plug in the values for A, and you end up with an internal energy of about 456,000 joules. Do the same thing for B, 3/2 nRT, the difference being the temperature of B is higher. Plug in our values, and we end up with about 503,000 joules of internal energy at B. So this quantitatively agrees with what we just thought through, that this number should be a higher value than the number on the left. The internal energy has increased. Part D is where we're going to start the next video for this example. So we'll stop this video here. Make sure you check out the second video for the rest of this problem.